Have you ever felt like you're just, drowning in information? Like you're constantly scrolling, reading, trying to keep up, but the sheer amount of data makes it almost impossible to truly understand anything quickly. It's a problem we all face, right, in this digital age. Well, today we're going to cut through some of that noise. We're exploring a really groundbreaking invention, something that promises to make sense of massive, multi-dimensional information. Our mission today is to do a deep dive into this system called the Fractal Identity Map, or FIM for short. It's described in a recent utility patent application. Think of it as maybe a shortcut, not just to being informed, but profoundly informed. We're looking at how this new architecture is redefining how computers, and maybe even us humans, can grasp really complex information. It's about finding some clarity in all that chaos.
Exactly. And the core challenge this invention tackles, it's pretty fundamental. How do we organize data so it's both incredibly efficient to process and easy for us, for humans, to understand? Most existing methods, they kind of force you to choose. You get one or the other. Take geometric indexing, things like Hilbert curves. They can pack lots of dimensions together, sure, but they often scramble the meaning in the process. They, lack that inherent explainability and struggle to adapt when data changes. Then you've got your tree-based structures, like the B trees common in databases. They work well for single dimensions, but they get pretty rigid when data shifts or when you need to see relationships across many categories. And okay, knowledge graphs can be rich semantically, but they tend to get messy, hard to scale, hard to parallelize. Even powerful modern techniques like neural embeddings, turning data into vectors, often they're a black box. They give you an answer, yeah, but not a clear why, and their meaning can drift. The firewall aims to overcome all these limitations kind of simultaneously.
Okay, so let's unpack this FIM system. It sounds revolutionary. You know how sometimes people say the map is the territory? Well, with FIM, it seems even deeper. It's about making space itself the symbol. What does that actually mean? So instead of data just being stored somewhere, its actual position within this special structure, this hierarchical, self-similar fractal structure, that position defines it. And here's the really clever part, I think. A data point's coordinates inherently define its semantic identity, its context. So every coordinate is, what, self-legending. You can literally understand what the data is just by knowing its location on this map. It's like the map doesn't just show you where things are, it actually tells you what they mean. Pretty wild.
It is, and what's fascinating is the central mathematical concept making this possible. It's a parameter they just call E. Think of E as like a master control dial for the whole system. Mathematically, it's the sum of the hierarchical depths across all the dimensions involved. So E equals then. But what it does is quite remarkable. E simultaneously dictates how much the system reduces search complexity, specifically, we're talking OCTN. It also controls the constant time explainability, which is OE, the potential for hardware parallelism up to E times CTN concurrent operations, and even the memory footprint. Essentially, E bounds everything. It makes the performance predictable even when you scale up massively. It tames the complexity.
Okay, now this sounds really interesting. The beating heart of the FIM. The consistent weight, walk, rank algorithm. You're saying this is a huge shift from how things are normally done. Most systems treat data storage units, the blocks, and the connections or relationships, the nodes, as totally separate things, right? But this algorithm fundamentally unifies them under just one rule, based purely on weight. Is that right? So imagine this dynamic, almost pulsing data structure. It's constantly reprioritizing information, not alphabetically, not by some fixed rule, but just based on the strength of connections between parents and children in the hierarchy. That must allow for incredibly intuitive navigation because the order always reflects the actual importance of relationships in the data.
Exactly. And to really understand that beating heart, there's a principle called Shortlex ordering. It's key. Shortlex basically means you sort things by length first, then alphabetically. So what happens in the FIM is the most significant data elements, the ones with the highest weight, they automatically get shorter, simpler codes, and they naturally appear first when you look through the data. It's like your most critical files just bubble to the top automatically. This mechanism is crucial for maintaining what we call semantic locality. Related ideas stay physically close in the map, even as weights shift dynamically. And that, in turn, enables those really intuitive navigation patterns you were just talking about.
So what does this mean for performance? You mentioned complexity reduction. The invention uses something called multiplicative pruning via orthogonal decomposition. Sounds complex. Can you break that down? It dramatically shrinks the search space you need to look at. So instead of sifting through every single possibility, which could be, astronomical, you only focus on the relevant categories. Okay, let me try an analogy. Is it like searching a massive library, but the system instantly tells you Ignore floors 3, 5, and 7 entirely. They're irrelevant to your query before you even step foot there. So it's not just a bit faster, it's like an exponential leap. Achieving linear information gain. AAHANS log QC.
That's a great analogy. Yes,
Yeah.
that's the essence of it. You discard irrelevant possibilities wholesale, multiplicatively across dimensions. And building on that efficiency is another breakthrough, the semantic address bus architecture. This isn't your standard memory address. It's much smarter. It's a hardware-software interface where the coordinates, the prefixes, do double duty. They act as routing information, sure, to find the data, but they also act as self-documenting semantic labels. They tell you what the data means. This dual function enables something called unified skip logic. What that means for you, practically, is the system can activate only the memory banks that hold relevant information. It can literally power down the rest. For sparse queries, where you only need small bits of scattered info, the power savings can be huge. We're talking potentially 93% or more. The dynamic weight-based decoding essentially guides the system, course-defined, straight to what's needed.
Wow. Okay, but with all this dynamic shifting based on weights, how does it stay stable? Doesn't mean you just drift all over the place. That brings us to the threshold-based stability mechanism, right? So you've got this map constantly evolving, things shifting based on weight, relevance. This mechanism stops it from being like continuous, unpredictable chaos. It only triggers a reclassification, a significant shift, when the accumulated weight changes cross some predefined statistical threshold, like TUPRIFT plus T-STRIFT. That sounds crucial. It ensures predictable behavior over time, and it gives you an audit trail. You can see when and why something's meaning or position changed. So meaning stays kind of anchored until there's real statistical evidence for a shift. All right, this is all very sophisticated engineering. But what does it mean in the real world? Let's make it tangible. How about medical diagnosis? Imagine a doctor asking something complex, like find respiratory conditions in pediatric patients who also have abnormal blood counts. Carries. Traditional systems might choke on that multidimensional query. How does FAM handle it? It maps it to a specific coordinate, you said.
Right.
Like S2.1, P1.3, T3.2, and then explores only a tiny fraction of the data. But the key thing, maybe, is that it provides a clear, explainable path. Like, okay, we looked at breathing issues, then children, then blood anomalies. You don't just get an answer, you get the logic. That must be vital in healthcare.
Absolutely vital. Explainability is key there. And moving to another domain, like supply chain optimization, the efficiency gains are just staggering. We've seen figures like an 847 times reduction in complexity just from unifying how data blocks and their connections are ranked. And that translates directly into speed. Incredibly low latency. That beating heart algorithm we discussed with its recursive weight updates, it can enable query responses in around 12 milliseconds. Even for complex tasks. Here's a concrete example. Analyzing inventory across different regions for, say, over 1 million unique products, 1 million SKUs, traditional ERP systems. That might take 45 seconds, maybe longer. With the FAM approach described, it's potentially a 12 millisecond response, a 3,750 times improvement. That completely changes the game for global logistics.
12 milliseconds versus 45 seconds. That's incredible. Okay, one more application, and this one feels like science fiction. Brain-computer interfaces, BCI. The claims here are pretty astonishing. Ultra-low latency, less than 5 milliseconds from capturing a neural signal to outputting its meaning. And very high classification accuracy, like 94.7% for understanding 4 different types of motor imagery, just from brain signals. And the power efficiency, this is maybe the biggest number. Only 1 milliwatt per 1,000 neurons. That's 1,000 times better than CPU-based deep neural networks. This sounds like the kind of technology that could actually enable real-time, explainable control of advanced prosthetics, making them feel truly responsive, intuitive.
It really does open up possibilities there, which naturally leads to the question, if this is so powerful, why hasn't it been done before? The non-obviousness, the reason it's a genuine invention, seems to lie in how prior art, existing tech, actually taught away from this specific combination. Think about traditional database indexes like B-trees. Their whole design philosophy is about maintaining balance. Rigid balance for fast, consistent lookups. They actively discourage the kind of dynamic, weight-based reordering the FIM uses because, well, it could destabilize their structure. And similarly, many classic weight-based algorithms like Dijkstra's for shortest paths, they tend to explore options broadly first, breadth first. They usually avoid the kind of depth first, hierarchically prioritized exploration FIM seems to use. The FIM cleverly unifies these seemingly conflicting ideas.
So it wasn't just about putting pieces together. It was about combining things that conventional wisdom suggested shouldn't be combined or wouldn't work well together. And that leads to these unexpected synergistic results, right? That beating heart mechanism, unifying blocks and nodes under one dynamic weight rule, doesn't just add up the benefits, it multiplies them. the overall performance gain is way bigger than the sum of its parts. So it's not just tweaking existing tech, it's creating something fundamentally new that performs vastly unexpectedly better. We used a great metaphor in our prep for this. The FIM allows systems to sail faster than the semantic wind. Can you explain that? It's because statistically independent blocks of data, these chunks, can act like near whole new dimensions, and that multiplies the pruning effect. So the system harnesses this mathematical property, orthogonality, to get exponential gains that go beyond just the raw complexity of the data, like a sailboat using the angle of the wind, the apparent wind, to go faster than the actual true wind speed. It's a really cool image.
It is a powerful metaphor, and it leads to a profound benefit that isn't just about speed or efficiency, it's about addressing blind spots. In many systems today, especially the black box ones, if the designers didn't consider certain data relationships, or if a user's query overlooks a key dimension, those gaps are completely hidden. You simply don't know what you're missing. Potential biases, unexamined trade-offs, they're invisible pitfalls. But with FEM's unified structure and its explicit skip logic, these blind spots become, well, aware voids. Ooh. You can actually see them in the semantic map as sparse areas or gaps. You can see the paths not taken, the trade-offs not considered. This turns potential oversights into explicit, auditable choices. It empowers more ethical design, more creative exploration, because you're aware of the boundaries. It's way beyond just saving hardware cycles.
Okay, so let's bring it all together. What does this all mean for you, the listener, the person trying to make sense of the world? This deep dive, I think, has shown how the Fractal Identity Map aims to transform complex, high-dimensional data, taking it from being this chaotic flood into something navigable, interpretable. It's about more than just speed, isn't it? It's about building systems you can actually trust, understand, and maybe even intuitively explore.
Exactly. This ability to mathematically transmute raw spatial data into dense, meaningful symbols. We've been calling it mathematical symbologenesis. It sounds fancy, but it's about creating meaning from structure. And that ability is potentially unique. It directly tackles that fundamental challenge of information density. It could allow both humans and AI agents to make meaningful choices in systems that would otherwise just be overwhelmingly complex and opaque.
Yeah. We've seen how this invention isn't just about sorting data better. It's potentially about providing a clear, explainable pathway through incredibly complex problems, whether that's understanding brain signals or optimizing global supply chains or diagnosing diseases. For you, it points towards a future where maybe deep knowledge, real understanding, isn't just for a select few experts. Maybe it's accessible to anyone who can navigate these new kinds of self-describing semantic maps. So here's a final thought to leave you with. If the very structure of data can encode meaning, and if every skip path, every pruned branch reveals one of these aware voids, what new kinds of insights, what new ethical considerations, what innovations might emerge when we can literally see the boundaries of what we're choosing not to explore? What possibilities are hiding in those newly revealed voids of knowledge?